Hey Chem 20s, I'm going to give you a quick run through here on our next lesson in the review unit that's reviewing what we took in Science 10. So we're going to talk about chemical reactions here, and I'm just going to go a little ways into this, but not too far, because we don't need to go too deeply into that. So we're going to talk about chemical reactions. So again, we're in that process of going from small to big. So we talked about atoms and ions, protons, neutrons, and electrons. That's pretty small. We just finished talking about ionic and molecular compounds, so how atoms and ions come together to form compounds. Now we're going to look at how compounds and elements react in what are called chemical reactions. Just by way of ensuring that everybody's on the same page, let's just refresh our memories on some of these ideas here. So the types of reactions that we have are physical. The products are the same as the reactants, usually indicated by a change in state. So that would be something as simple as ice melting into liquid water. So we have solid ice, liquid water. The entity that's involved in that all the way through is water, but it's just done a change in state, and that's it. Chemical reactions occur when the products are different from the reactants. Then there might be a color change, an odor change, a state change, those kinds of things. But the ones that are really important for me is that you need to understand that the products are different from the reactants. Color change might occur, odor change might occur, state change might occur, but what happens for sure is that there is an energy change. Okay, so we have different products than reactants, and we have an energy change that takes place. Either energy is lost or gained. And when we get into Chem 30, we'll go a little deeper into that. Next, we have nuclear reactions, which we're really not going to talk about this year. If you take some physics, you've probably already taken some of this, or if you're doing Science 30 in the future, something like that, you might see these. The products, again, are different from the reactants, but there's a much greater release of energy in a nuclear reaction, and it involves either the splitting or the fusion of two of an atom. So either breaking it apart into two smaller atoms or taking two smaller atoms and fusing them together. We're not going to go deeply into that. So really we're going to be focusing right now on chemical reactions. This is called a chemical equation. In this case, it's a balanced chemical equation because it's showing these things here called coefficients, and it's showing what we started out with, which are called our reactants, and what we ended up with, which is what we call our products. Now, when we're looking at something like this, reactants turn into products, and the important thing, and something that a lot of students mess up, is you have to use that arrow right here. That arrow is super important because it's not like we're trying to create an equivalence like we would be in algebra. This equals that. This arrow is read as, I usually say, and this is going to come out terribly because I can't write with a mouse, reacts to form, or creates, or produces. Okay, that's what this arrow represents. So this reaction, if you don't recognize it, is glucose and oxygen reacting with carbon dioxide and water. This is the process of cellular respiration. And so we would read this as 1 glucose and 6 oxygens react to form or produce 6 carbon dioxides and 6 waters. A couple other things to point out. Other than the reactants and the products, which you guys should know from Science 10, don't forget about the state symbols. So there's solids here and gases here. So there's a solid here and 3 gases. Don't forget that we have solid, liquid, gas. Later on, we'll get into something called aqueous. And if we're really getting fancy, we might end up with a state like HI, which stands for Hawaii, or AK, which stands for Arkansas. No, I'm just kidding. The last bit here then is, aside from the state symbols, are these numbers in front of some of these entities. These are what we call coefficients, and they represent the number of moles of something. And we haven't reviewed moles yet. A mole is chemical amount. It's a way that chemists use to communicate the amount of a chemical used or created in a reaction. If you don't see a coefficient in front of it, just like we would see over here with the carbon, we just assume that there is one of these. So one glucose, just like there is one carbon in carbon dioxide. There are 5 types of chemical reactions that we discussed in Science 10. There are what are called formation reactions, when a compound is made from its elements. There are decomposition reactions, when a compound is broken down into its elements. A single replacement reaction that involves an ionic compound reacting with an element, could either be a metal or non-metal element, and it produces a new ionic compound and a new element. And then we have a double replacement reaction, which is involving 2 ionic compounds to produce 2 new ionic compounds. And finally, we have a hydrocarbon combustion reaction, which involves a hydrocarbon, an entity containing only, or a compound containing only carbon and hydrogen, being reacted with oxygen, producing carbon dioxide and water vapor. So, that was a really quick breakdown of the types of reactions. I'm going to get into this again with you when I see you next, so don't panic if that was way too quick for you. What I really wanted to get into today is balancing chemical reactions and giving you guys some time to try to remember and refresh your memories on how to do that. I'm going to introduce some stuff to you right now, but this is certainly not everything you need to know. You'll get to do a bunch of practice with this later on, and when I see you again, I will introduce you to some cheats, some interesting ways to look at how to do balancing in lots of different situations. So, balancing chemical reactions is all about the law of conservation of mass, which states that matter in a closed system will remain constant even if disturbed. What it basically means is what goes in must come out. If 3 atoms of hydrogen go in, 3 atoms of hydrogen have to come out in the product side. If one oxygen atom goes in the reactant side, 1 oxygen atom has to come out on the product side. We have to make sure that the things that go in come out. The number of atoms of an element that is on the reactant side must equal the number of atoms of an element on the product side. You must be able to do this in your sleep. By the time we get to our last unit, which is on stoichiometry, and I'll tell you what that means later, it has a lot to do with chemical reactions. You have to do this with really even not having to think about it. It just has to be done. So this is why we're going to get some practice in with it now, so that when we get to that stage, you'll be ready to roll when it comes to balancing. So I'm going to show you how I do this. A lot of people can get to the point where they do this in their head and don't really need to work this out longhand. However, I think it would be best if I sort of demonstrated on a few examples here how to do this. Basically, you want to treat your reactants separate from your products. And so when you're reading something like this, you're reading this as, right now, there's 2 hydrogens here, there's 2 hydrogens here, there's 2 oxygens here, but there's only 1 oxygen here. So we can see that this is an unbalanced equation. So in order to balance, I start to create a tally. So I'm going to start out with my hydrogens, and again, I apologize for the terrible writing. So hydrogens on this side we have 2. Oxygens on this side we also have 2. Jumping over to the product side, hydrogens we have 2 again, and we know, because I just told you, that on this side we only have 1 oxygen. So the thing that is not balanced are the oxygens. So in order to change this, we can't just go and put a 2 here and call it balanced, because that changes the reaction. If we put a 2 here, which is incorrect, we no longer have hydrogen and oxygen making water. By putting a 2 here, we have hydrogen and oxygen making hydrogen peroxide, which is not the reaction that we're worried about. So I'm going to just go and erase that little 2 there and get back to my pen if I can. There we go. So what we have to do instead is we use coefficients. So coefficients, if you remember, are those numbers that we put out in front of the entities that are involved in a reaction. So if I need 2 oxygens, what I have to do is I have to use a coefficient of 2 to basically tell me that there are two now water molecules that we're dealing with. One water molecule and two water molecules. So if I've got two water molecules now, that gives me 2 4 oxygens, or hydrogens, pardon me, and now I have 1 2 oxygens. So now I've balanced my oxygens, but in the process of doing that, I've messed up my hydrogens. I now have 4 here, but only 2 here. So in order to do that, we jump back to this side, and we put a 2 out in front of this hydrogen. Now that gives me 2, basically if you look at it this way, it gives me 2 hydrogen molecules. Each hydrogen molecule has 2 hydrogens in it for a total of 4 hydrogens. So if we look at our tally, we have 4 hydrogens here, 4 hydrogens here, 2 oxygens here, 2 oxygens here, and it's balanced. Okay? In this next example, it's already balanced for us. We have 2 hydrogens and 2 oxygens on the reactant side, and we have 2 hydrogens and 2 oxygens on the product side. So that one was already given to us as balanced. By the way, this is a formation reaction. We have elements reacting to make a compound. This is a decomposition reaction. We have a compound breaking down into its elements. So the same procedure is going to take place all the way through here. We're going to basically start to do tallies on either side and modify using coefficients to figure out how the balancing works out. I'm going to skip this one because it's relatively simple. Let's move to this one. So we'll start our tally. We have, that's an A, we have calcium, and there are 3 of them on this side. We have nitrogen, there's 2 of them on this side. We have chlorine, and there is 1 of them, or sorry, 2 of them on this side. Over on the product side, we have calcium again, and there's only 1 of them. Okay, we have nitrogen, again, there are 2 this time, and we have chlorine again, where there are 2. So my nitrogens and my chlorines are balanced, but my calciums are not. So we have to do something there. So we're going to modify the calcium chloride here by putting a 3 in front of it. That changes the calcium to 3, but then it also changes the chlorines. There are 3 times 2, which is 6 chlorines now. So that's a poorly drawn 6. Now that throws, we've got calciums balanced and nitrogens balanced, but our chlorines are not balanced. So what we're going to do to combat this is we'll put another 3 out in front of here. That gives me 3 times 2 is 6 chlorines, which gives me 6 chlorines, and now everything's balanced. Okay. This one's even more complicated. The only piece of advice I'll give you on this is if you have a polyatomic ion, and in this case we have 2 polyatomic ions, there's 1 there, and there's 1 there. If you see this polyatomic ion, which is ammonium, if you also see it over on the product side, then treat it as one entity. Don't break it apart into nitrogens and hydrogens. Treat it as just collectively as an NH4. Same thing with the nitrate. I see nitrate over here. I also see it here. I'm not going to break it apart. Now, this was kind of a stupid example to use, but if we look at this as it is now, treating these as individual entities rather than individual elements, I see 1 sodium and I see 1 sodium. I see 1 chlorine, I see 1 chlorine. I see 1 NH4 and I see 1 NH4. I see 1 NO3 and 1 NO3. So those are all balanced. And so we don't have to use any coefficients to modify that. Okay. I think I'm going to skip over these ones because I'd rather explain them to you in person. With respect to these are the hydrocarbon combustions. If you want to jump ahead to these on the worksheet you're about to get started on, just remember this, CHO, C-H-O. Balance your carbons first, then your hydrogens, and finally do your oxygens. Or do it in that order, and you should be able to do it. You may have to go back, and you could start with 1 carbon or 1 of your hydrocarbons here, see how it works out. If it doesn't work out, if you can't seem to use a whole number coefficient to balance the oxygens, then you might have to double your hydrocarbon. Okay, that's 15 minutes worth of me talking at you. What I'd like you to do now is you're going to get started on a worksheet to give you some practice, and then when I see you next tomorrow, we will jump back into this and see how everybody did. You don't have to learn it today. It's a process of reviewing, trying to remember how you did it, and see if you can't make some sense of this. So good luck, and we will see you tomorrow.